Yeah, if you like it.
No, I don't.
Yeah. So, but I think it is quite natural to. I mean, if you have a birational map on P2, automorphism on P2, then the strict image is. Yeah. Okay. So. In all cases, I will tell you, and there are definitions in books which are very accurate. So let us continue. We have birational automorphisms. We have their exceptional divisors and indeterminacy points. There is a very standard birational morphism, not automorphism, just morphism, which is written, for example, in a Hartshorn book, so probably you know it. So example, f from blow up of a point of x to x is a birational morphism. So there is an open subset which is complement of x to E, which is isomorphic to x minus the point P. So it is an isomorphism on open subset, and it is a regular map. There is an inverse birational map from x to the blow up, which is defined here. Just it is defined on an open subset of x, and there is a point of indeterminacy, and there is an exceptional divisor here. So theorem which explains how all birational automorphisms of surfaces look. Strong factorization theorem. If x is smooth projective and f is a birational automorphism of x, then there exists a commutative diagram v, x, y. So this is our, sorry, not y, but also x. X. This is our birational automorphism, and here we have two maps, P and Q, which are birational morphisms, and they are just compositions of several blow-ups in points, P and Q. Of blow-ups. So, for example, here we can blow our 3 points of indeterminacy. So we have this picture, Lx, Ly, Lz. Let us blow up 3 points. Ай! Ой, у нее разные ноги. Теперь не знаю, что делать. Она... Может быть, наоборот. Да. So we have these 3 points. 1, 0, 0, 0, 1. 0, 0, 1, 0, 1, 0. And we just blow up these 3 points. So what we get here, these are strict preimages of our Ly, Lx, Lz. And here are new exceptional divisors. Probably E1, E2, E3. We have our birational map F, which, so let me write it this way. Let me call this point probably no. So the point 1, 0, 0 maps to this point. Sorry. Yeah. So 1, 0, 0 maps to a line. It is the image. So this is Q, blow up Q. This is blow up P. This line is Q of E1. Ly maps to this point. Lz maps to this point. These are images of Lx. So I just want to say that this line blow down to this point. This line blow down to this point, and this line blow down to this point. So just yes, yes. So these are yeah. This is E1. Probably it is E2, E1, E3. Just this. Okay, so you can do it yourself and just observe. Here we have a composition of blow-ups. Here we have also composition of blow-ups. This is V, this is X, this is X. So now we can define. So our goal is to construct Pizo and Salem numbers as some characteristics of birational automorphisms. V is this blow up of 3 points. It is P2 blown up in 3 points. So you can. Yes, yeah. So, or it is Edelpezzo of degree 6, if you want. Yes. So now, given a birational automorphism of P2 or of X of any surface, we can define an operator back on Neron-Severi group of X. How do we do this? We have our birational automorphism. We construct some resolution of its indeterminacy. So a variety, a surface P, and birational maps P and Q such that the diagram commutes. And we just define F inverse is composition P direct image, Q inverse image. So we take a divisor here, we can define a divisor on V, and then we just take its direct image on X. It is also be a divisor. So it is somehow defined. So lemma. As you can see, this definition depends on the choice of this variety V and birational maps morphisms P and Q. So in fact, the construction does not depend on this choice. for any V, P, and Q with this property, you will get the same operator here. Yes, yes. Yeah, so for each divisor, we can compute its preimage. Okay, for a general divisor, so any class here is a sum of linear combination of ample divisors. You can take components, just choose a representative of ample divisor which is away from indeterminacy point and just yeah, so let us do it here. Yes, and using such a way, it is easier to do here because yes, so we should just compute a preimage of a general. So first of all, remember that neuron-Severi group of P2 is Z. And we want to compute this operator. So consider the class of a general line. So x plus ax plus by plus z cz equals 0. If we compute its preimage, it will be a curve given by the equation a yz plus b xz plus c xy equals 0. It is a quadratic. So line goes to a class of quadratic. So it is just multiplication by 2. On the other hand, we can compute the action of pullback of square of f. So f squared pullback ns of P2. And observe, so f squared is just identity. So it is isomorphic to z, and this map is just multiplication by 1. So you can see that the inverse image, so f have no action on neuron-Severi group. We just don't have this property that f squared and also to any power n is not equal to pullback of f to power n. So this is a problem. So identity, yes. Identity maps line to line. Yeah, so we don't have equality, but still we can compute some number related to a birational automorphism. Yeah, so there are several ways to do it, but so I prefer the following one. Let's choose a norm on neuron-Severi times r of x. So we have many norms, but all of them are equivalent. Then we can compute, so given our automorphism, we can consider its pullback and compute the norm of this automorphism. So we consider all iterates of our automorphism, compute norms of their inverse images, square nth root and compute the limit. Just a vector space. Да, на векторном пространстве. Yeah, so this will be some number.
Is it like dot product which you have in counting, or is it totally different norm? Like maybe totally different norm?
Probably a completely different norm, yeah. Just any norm. So it is a finite dimensional space.
Oh,
so
okay.
all norms are equivalent up to some constant. They give. Yeah. And in fact, the limit won't depend. So this is what yesterday was called d1 of f. Sometimes it is denoted lambda 1 of f, but it's all the same. It is first dynamical degree.
But the limit exists. Yeah, you didn't explain why the limit exists.
Yes. It is.
An exercise.
Yes. Да, именно в них. This is called first dynamical degree, and the theorem which we already had yesterday, theorem by Dean and Sibani, says that the limit exists and it does not depend on Dean Sibani. D1 of f is correctly defined. Does not depend on the choice of norm. And does not depend on the choice of the birational model. So x, we take x and compute the limit for action of inverse image on neuron severe group of x. But if we take some birational model y, and here is induced some fy, we can compute the same limit for this pair, and we will get the same number. Of x. So it is some birational invariant of x. Let's look at our example. Try to understand what do we have here. So as we computed, да, ну, один и тот же. Okay, so f, let us compute the norm of f, of pullback of f. Pullback of f acts on neuron severe group by multiplication by 2. So we can, so one-dimensional space, there is just one norm up to multiplication by a constant. Let's use it. So the norm of f equals 2. The norm of f squared pullback, it is identity. So this norm equals 1. Moreover, for each k integer, the norm of f to power 2k equals 1. And norm of f to power 2k plus 1 equals 2. So here we have d1 of f equals limit square n of 2 or 1. So this goes to one. So in this example, the dynamical degree equals just 1.
I assume that it should always be 1 because you say you can regularize it so that you're using a series of blow-ups, and for a regular map, the pullback of composition is composition of pullback.
Not,
you cannot regularize it.
yes,
You can
not
regularize
any
it
birational.
You use the word regularize in 2 different senses at once. That makes a mistake.
So another example, we have P2 to P2, and a birational automorphism which is defined on just a chart. Wait, sorry. Here we have coordinates x, y. F maps it to y x plus q of y, where q is a polynomial c of y, and degree of q greater or equal than 2. What? So this is f. So you can. I want to say that then degree of f probably f to power n of x, y is given by formulas p n of x, y, q n of x, y, where degree of Pn equals it equals d to power n minus 1, and degree of Qn equals d to power n. Why is it so? Just by induction. So for
Why d is the degree of q?
yes, it equals d. So just by induction, you can check that this is true. So then in homogeneous coordinates of f, the nth power of f is given by homogeneity of degree d to power n. So norm of f n pullback equals d to power n. And d1 of f equals d. It is an integer. So we have an example where dynamical degree is not equal to 1. Yes, so yeah. So another example, probably exercise. Example, birational automorphism from P2 to P2, which is defined on GM. Squared. So let us fix a matrix A, B, C, D in SL to Z. And we send X, Y here to X, A, Y, B, X, C, Y, D. It is a birational automorphism because the inverse matrix defines the inverse birational automorphism. And you can compute that d1 of f equals lambda, the greatest eigenvalue, yes. Greatest eigenvalue, so probably absolute value of A. So there are two cases, either two roots, so both eigenvalues of A are not real, but then they should be on the unit circle. So this is just a matrix of finite order. Or one eigenvalue is greater than one and another is less than one, and both of them are real. So d1 is either 1 or it is a quadratic reciprocal number. So there are many possibilities for dynamical degrees. We saw some of them, and so now we switch to we consider these three cases, and we discussed here birational automorphisms, but it is easier to compute dynamical degrees for regular automorphisms. So let us start with them. So next example, which will be longer there than previous, regular automorphisms. А сколько времени у меня осталось?
45 минут.
Отлично. So we have X and our automorphism F, which lies in group out of X. Then F acts by inverse image on neuron-Severi group. And it preserves the intersection form. Here we have a form, and we know that this inverse image lies in orthogonal group with respect to this form. By Hodge index theorem, no, just yes, just if your automorphism is regular, then you preserve the form because it is so okay.
What is the definition of regular automorphisms?
Just regular, just algebraic isomorphisms. Yes.
And now your brackets to the comma is an actual intersection form.
Yes.
Okay.
On surface. By Hodge index theorem, the signature of this form is 1 m. I want n. Just one positive and a negative. So in order to study dynamical degrees of regular automorphisms of surfaces, we have to understand how this group. Yeah, so let me give some more definitions. We will say that R1n is Minkowski space. If it is R1 plus n, probably plus m, with a quadratic form, symmetric form, such that I хочу m. Here we have a hyperboloid HM, which is the set of all x in R1M, such that x equals 1. So in fact, we have two components of this hyperboloid, but we take only one of them. So this is component. This is just.
And what's the dimension of the space?
1 plus m. Okay, yes. Component of this hyperboloid, which contains the vector 1, 0, 0. There are two of them. And we take one which contains this point. So any automorphism which, I just want to say that our regular automorphism of a surface, it does not only preserve this form, it also preserves an ample divisor. We can ample divisors lie only on one of the two components. So that is why we are interested in the following. We say that isometries of, we are interested in the group of isometries of HM, which is group of all H inside O of 1M, such that H of M is itself. So probably H can map HM to another component of this set. But we restrict to this index group. These isometries are of two types. So theorem, let H be an isometry of HM. Then H is one of those.
Just any isometry, not necessarily coming from.
Yes, any. So this is just theory of hyperbolic spaces. So the first one is as follows. There exists a vector u inside HM such that h of u equals u. So we have a fixed point on the hyperboloid. This type is called elliptic. So these three classes will be not intersecting. So the second one is non-elliptic, but there exists the vector u, which is isotropic.
And in the first case, it wasn't isotropic?
It is on Hm. So Hm contains only those whose square is 1.
Okay.
Which is such that h of u equals u. Не нулевой. And third, there exists чего? Может быть. Нет, оно изотропное. Не существует. Давайте сейчас я.
У нас есть решетка, у нас есть пространство, у нас есть вектора с квадратным мотивом. Это 3 раза объект, у нас всего 2 раза обозначения.
Сейчас. Какие обозначения вы хотите?
Значит, это изучает автоморфизм векторного пространства.
Векторного пространства. Решетки у нас тут нет. Тут у нас нет решетки. Только вектора, да.
Но H это автоморфизм всего пространства.
Всего пространства.
Тогда нам надо написать не...
Я определила изом HM как все H из O1M такие, что они сохраняют компоненту.
Хорошо.
Ура! Ну ладно, он приводит обильный в обильный, да. Он приводит обильный в обильный, то есть... да, все. Я соврала. Молодец, ура. There exists U, which is isotropic, and such that h of u equals lambda u for lambda inside R greater than 1, strictly greater than 1. There exists some real number which is greater than 1, which is eigenvalue of h, and u is eigenvector for this eigenvalue. So let yes, non-zero. Thank you. Okay, so let me give some idea of proof, or maybe the proof. Yeah, thank you. Yeah, so it is parabolic, and this is loxodromic. Русские, мне кажется, его называют гиперболическим. Вот третий тип. Мне кажется, слово локсодромический по-русски не существует. Но по-английски обычно loxodromic. Вот это. Он же, да. Hyperbolic. But this word is never used. Okay, so proof. So we have our space R1M. Consider the complement to 0. Then we can map this to the projective space Pm. Just this is the projectivization map. HM maps to its image P of HM, and this map is an isomorphism. Because for any x inside HM. So the line passing through X intersect HM only in one point with X. All proportional will be of won't be of square 1.
What if we multiply by -1?
Нет, у нас еще x0 больше 0 требования. Важно, что у нас
Да,
больше 0.
да, да, это компонента. This is real projective space, and this is a subset given by the formula x0 squared is greater, no, is, yeah, greater, less, okay, greater than x1 squared plus etc. plus xm squared. I just want to say that this is just disk. This is d to the power m. And so there exists a point P inside dm closure, which is fixed. So here we have our isometry H. It induces a map on the projective space. Isometry preserves HM, so here it preserves the image of HM. So it preserves this disk, this closed disk. And by fixed point theorem, there exists P such that H of P, so probably P H equals P. So then there exists a vector u inside R1 m, and such that either u equals 1, or you can just check that. So the boundary of this disk is contains of all x such that x0 squared equals x1 squared plus xm. So these are images of isotropic vectors, or u equals 0. Yeah, so there exists such u, which is an eigenvector. H of u equals lambda u. First, assume that u, if u is inside Hm, then its square is 1, and the square of its image should be also 1. So then lambda equals plus or minus 1. And if it is minus 1, then u goes to another component of these two hyperboloids. Then lambda is just 1. And we're in the first case. So we get elliptic automorphism. And then there are two possibilities. Either, if u such that it is isotropic, then either lambda equals 1, or lambda is not 1. If it equals 1, where in the if it is not equal to 1, it remains to show that the eigenvalue will be a real number which is greater than, there exists. So first of all, I just want to say that if lambda is not equal to 1, then it is real, because we preserve the real line. So it can't be negative because we preserve the component of hyperboloid. So it should be positive. In second case, either lambda equals, either lambda is greater than 1, or it is between 0 and 1. It is real. It is not negative because we presume HM. So you can just, yeah, it is probably not obvious, but it is the same argument as here when we showed that here lambda equals plus 1. Yeah. Потому что компонент туда сохраняет. Поэтому он сохраняет конус. В частности, вот у нас есть конус квадрат u равен 0. Это вот такой вот конус. Давайте выкинем из него 0. Он развалится на две компоненты. И наша изометрия либо...
Даже на больше, на 4, кажется.
Ну, он кругленький такой, в смысле, если у нас достаточно большая размерность. Вот, он развалился на две компоненты, и наш автоморфизм, он либо сохраняет обе эти компоненты, либо переставляет. Но если он их переставляет, то вот гиперболоид, который сюда вот так вот вложен, переставляет вот в этот гиперболоид.
Почему он положительный? А почему он
сохраняем прямую. Мы сохраняем вещественную прямую. Мы знаем, что u переходит вот в этом пространстве. Что 0? Почему? Потому что, да. Okay, so either lambda greater than 1 or lambda is between 0 and 1. I just want to say that in this case there exists, so we know that where in this group, so the determinant of the matrix A should be 1. So the product of all eigenvalues should be 1. So if we have an eigenvalue which is strictly less than 1, then we should have an eigenvalue which is greater than 1. Consider the eigenvector which corresponds to this eigenvalue.
If all other eigenvalues are complex?
Yeah. You didn't discuss the...
Okay, Frobenius-Perron theorem. Sorry, this is so difficult to use.
Assume this ISO and an automorphism. Okay. So I guess this lambda can be taken as the maximum.
But why is it real? Why is it real? It is real just by... Yes, it is Perron-Frobenius. Yeah, so theorem Perron-Frobenius. Assume that we have a vector space V isomorphic to R n. Here we have C, which is a cone, convex, convex. So it does not contain line. Okay, sorry. Convex cone, and we have F inside GL of V such that F of C equals C. Then there exists lambda eigenvalue which is real, probably S, which is greater or equal to 1, and there exists an eigenvector V inside C such that f of v equals lambda v. So it's just some linear algebra theorem, quite easy, but still not trivial, which says that in this case we will have a real eigenvalue greater than 1, and so then the eigenvector
is closed.
Closed, yes.
So this just says that we have some real eigenvalue.
Yes,
We
yes,
know
exactly.
That's why it's greater than 1.
So here it is greater than 1. So, and this lambda is the spectral radius. It is greatest eigenvalue of f. Лежит. У нас совпадает.
No, if you want to do spectral radius, you need some more assumptions. Like if C is just a line corresponding to another eigenvector, which is for which the eigenvalue is not the maximal, then you need some assumptions.
Okay.
Maybe it's non-infinite future.
I don't want to be. So
No,
What you ask?
what is written is just wrong, because you take a line with eigenvalue less than 1,
Yes.
and take it as C.
No, it's open form. Yeah, I mean.
я не поняла. Я вообще не понимаю, чего вы говорите.
Мы говорим еще раз, что то, что написано неверно, потому что
Почему?
можно взять в качестве конуса одну прямую.
Да, но это в слово конвекс входит вот все вот это.
Нет, не входит.
Вот я вложила. Хорошо, конвекс полноразмерный. Полноразмерный.
Special linear. I mean, in general linear. Okay. And why this?
No, because otherwise you can take a scalar which is less than 1 and
Yeah,
1
so
over 2 and multiply everything.
I want the greatest eigenvalue, which is greater than 1 in particular.
Just for being greater than 1.
Yeah, but I mean it's GL.
No, just multiply everything by 1 over 2.
I mean.
It will preserve all points.
I mean, but for the automorphism, always
Yeah, everything is an O. It's an terminal, so it's.
Там есть какая-то выделенная прямая, на которой первое свойство значение, и конус с ней не пересекается?
Конус с ней сейчас вот тут.
Да.
Конус ее содержит.
Окей. И ну,
У нас просто мы сохраняем конус. Тогда, ну вот по этому аргументу из теоремы Брауэра у нас есть неподвижная точка. И там нужно немножко аккуратно все проверить, но мы найдем направление внутри этого конуса, ну или на границе, которое соответствует спектральному радиусу. Ну, в частности, максимальное по модулю собственное значение будет вещественным. То есть, все.
Если мы применяем Фробениус Перрон, то уже Брауэр как бы не нужен, да?
Да, но чтобы доказать Перрона Фробениуса нужно. Да. Хорошо, следствие. We proved this theorem, this classification, almost. Corollary. If X is a surface and F is its regular automorphism, then lambda 1 of F, d1 of F, sorry, its dynamical degree is either quadratic, it can be, yes, it could be 1, quadratic, integer, or Salem number.
So now you write out. You still mean birational.
No, it is regular automorphism, yes.
Wait, in the theorem we did prove, and I don't understand if it's correct or not at all. So these three conditions are mutually exclusive, or we just
exclusive.
say so it's not possible to have both eigenvectors with.
For instance, compare condition 1 and 2. The beginning of condition 2 is that there doesn't exist something which exists in condition 1.
Aha, so theoretically there could be, but we just exclude it explicitly.
So, for example, identical automorphism preserve everything.
Yeah,
and it is elliptic.
Maybe we should exclude identical, but no, it's different.
Yeah. So there are rotations which.
Okay.
Okay, rotations.
This u in the second case, this one is already the maximum. It's already the spectral radius.
Yes. Yes. Yes.
These three happen. The third case happens. It still can happen that there exists some eigenvalue.
Yeah. Okay. Yeah.
So I guess this
So,
will be the spectral radius one.
Yeah. Spectral radius.
So when 2 and 3 are both possible, we call it 3 and not 2. Okay.
So here another condition. But it, so by Frobenius-Perron, we can see that we can find. So we just look for this eigenvector where we have the greatest eigenvalue, and either we get the eigenvalue equals 1, and we are here, or we find some lambda which is eigenvalue greater than 1. Yeah. So let me prove the corollary. So we have our automorphism. It induces the inverse image operator on neuron severity of X. And we know that the iterate of pullback equals iterate of the pullback. Pullback of the iterate. Okay. So then, just because, we have action on neuron severity group. The group of automorphisms acts here. I just want to say that d1 of f equals the spectral radius of f. F pullback. Let me explain this. This was mentioned yesterday, so now the proof. Yeah, so let norm on NS R of X be norm of, let me choose some basis, E1, EM, probably 0 EM, and norm will be just, so then the operator is given just by the matrix Aij in this basis, and the norm will be maximum of absolute value of Aij. This is a norm on, yeah, probably, no, I am just like, okay, so this is the norm of the operator of pullback. I don't want to introduce the norm on neuron severity group such that, so we know that this is an operator norm, which is related to some norm on the space. So now let us, instead of some basis here, choose the Jordan basis. So in some basis, pullback is just given. Probably we should complexify the space. It is given by lambda, which is the greatest eigenvalue, mu1, mu m, and here probably we have some 1 over diagonal. We have some Jordan blocks.
I don't like this norm. Imagine you have a matrix where all entries are 1. It's degenerate, of course, but I think that there are some vectors which become longer, which means that you should not call it norm 1.
Okay, we take this not norm and compute something, and then say that in general case it is the same. Just the computation a little bit more difficult. Yes. So compute f pull back to power n. This will be the following thing. We have lambda n here. We have mu1. Probably here we have n times mu1 to power n minus 1. So I believe you know what is the nth power of Jordan block. Here we have n k mu1 n minus k. For n very big, the norm of nth power of pullback will be lambda n, probably times some polynomial. If we have a Jordan block with eigenvalue lambda times p of n, which is a polynomial in z, so a binomial coefficient, in fact, z of n. We want to compute dynamical degree, so we should take nth root, and you can just see that this converges to lambda when n goes to infinity. So this fact is just linear algebra. Okay, now lambda is the spectral radius of not lambda, sorry, it is not lambda, it is d1. Dynamical degree is the spectral radius of the pullback. We know that this is a Minkowski space, and the pullback of f preserves the hyperboloid, as we discussed. So f is one of these three types. So if we are here or here, then the spectral radius equals 1. So the dynamical degree equals 1. If pullback is elliptic or parabolic, then d1 of f equals 1. So the only case is when f is loxodromic. Then there exists lambda eigenvalue of f pullback, it is pullback, which is greater than 1, which is real and greater than 1. Let me call so pullback of u equals lambda u. Assume that v is some class inside neuron-Severi groups. It's complexification, complexification such that pullback u v equals mu v, and mu is some complex number such that its absolute value does not equal to 1. Then, so I just don't want to explain this now. by Hodge index theorem, we can show that. So yeah, probably something I want to show. First of all, we know that self-intersection of U equals 0. What is self-intersection? So we can extend this intersection form to some Hermitian form on this space. U, V. It equals the product of pullback U, pullback V. It equals lambda U bar, mu bar, U, V. So we see that either U and V are orthogonal or lambda times U bar equals 0.
Equals 1.
0. 1. 1. Okay, yeah. U, V equals 0 or mu bar equals 1 over lambda. So arguing, yeah, and also we can compute the self-intersection of U and U and observe that this equals mu bar U. So then since the absolute value of U is not equal to 1, we get that U is isotropic. But V. Sorry, yes, you are right. V is isotropic. But by Hodge index theorem, if U is isotropic, V is isotropic, and they are orthogonal, they should be proportional. So this is not a new eigenvector with new eigenvalue. It is also U. So what I want to say is that there is root of tomorrow I will approximately, which is the minimal book. So this argument here. And you have, so is mu u plus u prime, and you just equal and
imенно just satisfy this assumption fn go back equal to f go back n, but f may not satisfy the homomorphism, but satisfy this condition. This may not be true, right?
Yes, it is not true because the form. So here this yes, yeah.
Because for surface we can always find such a conjugacy.
Yes.
Ну, хочешь?
А в смысле, а из второй теоремы следует, что не все числа состоялись?
Ну, возможно, это указывает на то, что более Салема нет. Что, может быть, найдут. Вот это да, минимальное известное. Да.
То есть, как выглядит образ чисел, которые возникают из специальных запутанных, они непонятны.
Ну, что-то понятно, но...
Не все реализуются, да?
Я не знаю, давай я завтра скажу, сейчас не знаю, не буду говорить. Да. Думаю, что сложно, не знаю. Я такого, по крайней мере, не видела. Да.
Я не знаю ответ на этот вопрос, но я знаю, что почти никакой вопрос Еще вопросы?
Сохраняется?
Композиции.
Нет, нет. Ну вот, например, чего вы хотите, чего именно вы хотите, но не как хорошо. Ну, то есть, например...
Ну, динамическая степень f композиция G...
Ну, даже спектральный радиус никак хорошо себя не ведет. Да.
Может, они себя ведут действительно как максимально количество предложений.
Да, просто, наверное, было понятно, когда мы f и f квадрат рассматривали с p2.
Ну, там как раз...
Как раз это верно.
Нет, почему там?
Динамическая степень.
Это 2. Динамическая степень f квадрат это не 2 умножено на 2.
Динамическая степень у них у всех равна 1, да.
Динамическая степень это
потому что
корня там.
А, да.
Не, ну там есть только неравенство, да, как бы. Вы можете перемножить, тогда будет не больше, чем...
А вибрационально даже это неверно.
Про то, когда там динамическая степень мультикативна при композиции. Это же специальная ситуация.
Мне кажется, типа почти никогда. Там про это, по-моему, есть утверждение, что типа если это выполняется, то значит одно это степень, один автоморфизм это степень другого.
То есть просто они растягивают один и тот же вектор в
Да.
место G.
Да. И более того, они абсолютно одинаковые, да. Мне кажется.
Нет
Ну вот есть утверждение про то, что если два гиперболических автоморфизма, то тогда это может быть только Z.
Это довольно понятно.
Ура.
Так, еще вопросы? Если нет, давайте поговорим с вашей